Okay, let's say, for example, let's say that for some magical reason, you know that we have an existing, let's say it's some sort of medical test, and the probability that this medical test, we could say it's, I don't know, some sort of test for a virus or something like that, right? Or a test for high cholesterol or something. You know, let's just, magically say that we know that this is accurate 99% of the time. 99% of the time. All right. And so what I'm going to do is I'm going to use this and try to develop an idea of what hypothesis testing is before we get into some formal definitions and terminology, all right? So if we know that this is accurate 99% of the time, then, we can compute some probabilities, right? So let's suppose that we apply the test 100 times. Apply the test to 100 people 100 times. All right. Do we, always just assume that it's accurate 99% of the time, and that we're going to, if we apply the test to 100, 100 patients, that 99 of them will be accurate, and one of those 100 will be inaccurate? Well, no, right? There's some wiggle room, right? You could get lucky, and you could get all 100 of them to be accurate, right? It's just in the long haul, we would expect it to be accurate 99% of the time, right? So we can compute these probabilities, right? We can compute these probabilities. Probability that if we apply the test 100 times, let's say that it's accurate 100 out of 100 times, and we get lucky. And I'd encourage you to think about doing this, but the point of this video is not to talk about binomial probabilities. So I've done these ahead of time. Take my word for it. So this should be about 36.6%. So definitely within the realm of possibility. What about the probability that it's accurate 99 out of 100 times? That is slightly more likely. That's about an even 37%, roughly. Okay. What about the probability the test is accurate 98 out of 100 times? That is about 18.5%. What if we get unlucky? How unlucky do we have to be for it to be accurate only 97 times and have 3 people's tests be inaccurate? That is about 6%. What about the probability 96 out of 100? That's about 1.5%. What about the probability of 95 out of 100 times? Well, with a test that is supposed to be known to be 99% accurate, the probability that we apply the test 100 times and it is accurate only 95 out of 100 times is about 0.3%. 0.3%. It is within the realm of possibility, but very unlikely, right? You'd have to be extremely unlikely for that to happen. Okay, so let's take that information and just kind of hold that on the side for a second. Keep that in the back of our minds. Let's say now you have a new test. You have a new test. A new test. Maybe something that gives you your test results faster. I don't know. Increasing efficiency is often reason to revamp maybe an existing test. All right. And for whatever governing body, whether it's, I don't know what the appropriate agencies are, the FDA, or that's probably not the right organization, but some sort of medical agency, in order for this to be accepted, maybe the CDC or something like that, we need to have the probability that it is accurate in order for this to be pushed forward has to be 99%. right? We need at least a 99% accuracy rate, right, on our new test, okay? Well, so how good do you feel about your new test? You need this to be 99% accurate, right? So what can we do? Well, we'll hypothesize the accuracy of our test. Create a hypothesis that the probability that the new test is accurate, is 99% of the time. That is our goal. That's our goal. So what do? We're going to go ahead and apply our new test 100 times. Apply it 100 times. And let's see, well, what happens. We apply the test 100 times. And let's suppose, after we apply the test 100 times, we take a look at the results, maybe verify it against some other benchmark that we know the true answer to, and we find out that our new test is only accurate on 95 patients out of 100. 95 patients out of 100. Well, what do we think? If we assume our hypothesis is true, then our observed outcome of 95 out of 100 is 3%. If we assume that this is 99% accurate, it is possible, but it's extremely unlikely. We assume the hypothesis is true, then what we observed only happens about 0.3% of the time. About 0.3% of the time. So with that low probability, you would likely say our hypothesis is wrong. Probably reject our hypothesis. Probably reject, not project. We probably want to reject our hypothesis. That it is probably not true. Probably not true. Right? This is assuming our hypothesis is true. It is technically possible, but it's extremely unlikely. And this is sort of the general idea behind hypothesis testing. Usually, as a statistician or someone working on a statistical test, you'll have some sort of level of cutoff. And where that cutoff is somewhat arbitrary, but usually it's somewhere along the lines of 5%, is very common. And so you might be looking at this hypothesis and saying, well, as long as I get maybe at least 97, and I have a cutoff maybe right there, anything below that, and it's too unlikely for me to assume my hypothesis is going to be true. And you have some sort of predetermined cutoff, and you calculate the probability that you see your observed value, assuming your hypothesis is true, and you can make a conclusion based on that. This is sort of the idea behind hypothesis testing. And there's a lot of formal terms that we're going to start to define here that are showing up in this test. Things like null hypothesis, alternative hypotheses. There's some p-values and things like that that you can get into. But this is just the general idea behind a hypothesis test, in that we will probably assume the hypothesis is true unless something really extreme happens. Really extreme happens. Okay? Let's go ahead with that sort of introductory example out of the way, and with the idea of what we're trying to do as we move forward here now on statistical inference in Chapter 10, let's go ahead and give us some formal definitions and things to take down in our notes before we move forward, okay? All right. So let's go ahead and define what our statistical hypothesis is. All right. A statistical hypothesis is an assertion or a conjecture It's an assertion or a conjecture concerning one or more populations. Concerning one or more populations. All right. Usually what we'll do is we have some claim about a population or a value of a population parameter, and we need to look at evidence that would either support or reject that claim. So we look at some sample data and try to reach our conclusions with a high probability of being correct. We want a high probability of being correct, and so that is why there's this asymmetry here, in the sense that I don't want to reject my hypothesis unless I am extremely confident that it is not true, right? So in the example that we had, if we assume this is true, this occurs only 0.3%. We can very confidently reject the hypothesis then. Very confidently reject the hypothesis because it is so unlikely for that to occur with the hypothesis being true. All right. Let's talk about the two pieces of hypotheses. There is the null hypothesis, N-U-L-L, null hypothesis. The null hypothesis is the statement being tested. The statement being tested. And we usually denote this as H sub 0 or H naught. Okay, this, when we're doing a null hypothesis, should be a clear and definite statement about a parameter. A clear and definite statement about a parameter. Often, usually it's an equation. Clear and definite statement about a parameter. So for example, we might say the null hypothesis would be that the population mean mu is equal to 200, right? Something that's clear and definite, usually using the equal sign, right? The null hypothesis, the probability the test is accurate is 0.99, This goes up against an alternative hypothesis then. An alternative hypothesis. The alternative hypothesis. The alternative hypothesis is the hypothesis that opposes your null hypothesis. So, for example, here, if we have the null hypothesis that the mean is 200, the alternative hypothesis, H1, would be mu maybe not 200, for example. And there's a lot more flexibility in your alternative hypothesis. All right. Or you could have something like mu greater than 200. A little bit more flexibility in your alternative hypothesis is allowed because our null hypothesis is so definite. All right. In general, we will arrive at one of the two following conclusions. Arrive at one of the two following conclusions. We will either reject the null hypothesis. When you reject the null hypothesis, this is done in regards to the null or the alternative hypothesis. We reject H naught in favor of the alternative. We reject it because of sufficient evidence. Sufficient evidence. You need serious evidence to reject the null hypothesis. Serious evidence to reject the null hypothesis. You either reject the null hypothesis or you fail to reject. You fail to reject it because of insufficient evidence. insufficient evidence. You either reject the null hypothesis or fail to reject the null hypothesis. All right. When we are failing to reject the null hypothesis, you are sort of by default, if you fail to reject kind of by default, I guess you're sort of accepting, but really what we're doing is we're failing to reject it, right? We're not proving that the null hypothesis is true. There's a fine line between the verbiage there, but when you fail to reject it, you're not proving it's true, you're just failing to reject it, all right? And if you do fail to reject it, again, by default, it's sort of accepting the null hypothesis, but you're not proving that it's true. You're not claiming the null hypothesis is true. You are just failing to reject it, right? But what you can do, what you can definitively say, is you can reject the null hypothesis. You can prove, essentially, or you can say with serious confidence that it is not true, right? You can say with 95% certainty the mean is not 200, right? Things like that is what we can do with hypothesis testing. That'll do it for this video. We will see you in the next.